Yeah, thank you, Paula. So today I'm going to talk about how to study big planets using tiny magnets. All right. How much can we learn about an entire planet or even the solar system from a rock? Even a rock as tiny as this one on this little slide here. That is the central question of my research program. I've been interested in planets since I was a child. I was always curious about why the Earth was so different. Why do we have oceans? Why do we have life? And why is every single other planet a completely different outcome? And I was so into planets even when I was like a toddler that when I graduated from preschool, my pre-kindergarten teacher gave me this book called My Picture Book of the Planets. And I read it so many times, it's taped back together, and I have to hide it from my son now because it has the wrong number of planets in it. And it even says Mars doesn't have water. So, you know, there's a lot of things going on there. But my interest in space and all things NASA persisted through my adolescence. I got to go to Kennedy Space Center. I thought for sure I would be on Mars by now. That didn't happen. But I get to work in this field. And the critical thing was I didn't know at that time that you could turn this into a career of studying planets. It wasn't until I got to college that I figured that out. And strangely, my interest in studying planets started with a very important question in studying Earth history. So there's this hypothesis, if you're not familiar with it, called snowball Earth, that hundreds of millions of years ago, and even billions of years ago, the Earth might have frozen over into a gigantic snowball multiple times in its history. And what blew my mind when I learned about snowball Earth was that a key piece of evidence that this event happened was from rock magnetism. Magnetism, what? How does this invisible field in rocks, how does that tell us that the Earth froze over and that this huge planetary scale event could have happened? Well, I'm going to walk you through it. So we know that the Earth has a magnetic field. You're sitting in it right now. It's about 50 microtesla strong. And it turns out that whenever you have rocks are made out of minerals, right? So some of these minerals inside your rocks are magnetic minerals. So on Earth, it might be iron oxides. On other planets, it might be metallic iron. You know, it depends. But regardless, these magnetic minerals, whenever these rocks initially form, these minerals are very hot. They're above their Curie temperature. And whenever these minerals cool below their Curie temperature, say as a lava flow is cooling down, if there's an ambient magnetic field present at that time, rocks can record the direction and the intensity of that ancient magnetic field. And that is what we study in our lab as paleomagnetists or ancient magnetism specialists. And a key thing is that not only can we record the direction, but the magnetization recorded in the rock is actually directly proportional to the strength of the magnetic field the rock formed in. Very convenient. So we can reconstruct that. And this remnant magnetization can be preserved on geological and solar system timescales. So let's go back to snowball Earth. How did we figure out that the Earth froze over? Or at least the hypothesis that the Earth might have frozen over. It turns out that the Earth's magnetic field, at least at the surface, kind of looks like a bar magnet with a north pole and a south magnetic pole. And the field lines follow the field lines of a bar magnet. So if you're at the north pole, the magnetic field, from your point of view, is vertical. And if you're standing at the equator, from your point of view, the magnetic field is horizontal, okay? And so based on that relationship of field geometry, we can say the tangent of the inclination of the magnetic field is actually 2 times the tangent of the latitude at which a rock formed. That's the dipole equation. And so back in the day, there were studies from rocks all over the world from this period in time called the Cryogenian. But there were these rocks in central Australia, these sedimentary rocks called the Alatina Formation. And they had these glacial deposits where these drop stones got plunked down from the bottom of glaciers and they landed in this marine sediment. And they used paleomagnetism, the magnetic directions recorded in these sediments, to show that they were deposited at the equator. Okay, so glacial deposits were placed at the equator. 650-ish million years ago. And that's how we know that this happened. That blew my mind. And so I got really interested in paleomagnetism, but the whole NASA thing, the space thing, I just couldn't shake it, you know? I had to do outer space. But I wanted to use these techniques because these techniques are so powerful. We can reconstruct all of Earth's plate motions for over 1 billion years using magnetism. Can we leverage these same methods to do outer space? And there's 2 ways to do this, okay? So I work on planetary paleomagnetism. And so the applications are, 1, we can study magnetic fields generated internally by planets. Or another application is to study the magnetic fields that were in the initial solar nebula or protoplanetary disk of gas and dust from whence all the planets initially formed. I don't have time to get into the second one today, so today I'm going to focus on how we learn about planetary magnetic fields. Planetary magnetic fields in rocky planets are generated by convection of metallic iron cores inside planetary bodies. And basically, the convection of the conductive core, coupled with the rotation of the Earth, generates a field that has a largely dipolar geometry at the surface, as we can see from Mercury as well as for the Earth. And this field is very useful in terms of planetary habitability and stuff because it protects our atmosphere and surface from charged particles in the solar wind that can, demolish gases that we care about. But what I work on a lot of the time is not the Earth, it's actually the moon. And why do we care about the moon? Well, the moon is this smaller body that it's like a natural laboratory for how do fields work, how long can they last? Because, it's gonna cool off faster, it might run out of energy earlier. Let's learn about this. So we wanna study, did the moon generate a magnetic field and how strong was it and how long did it last? That tells us about power sources. What is the moon's internal structure? Does it have a core? Did it have a basal magma ocean? How active has the lunar the lunar interior been over billions of years? In order to have convection of a core, you have to have significant heat loss. The planet has to be alive. And also what resources may exist on the moon, because the presence of a magnetic field can inhibit implantation of things we care about, like water, hydrogen into the lunar regolith, or helium-3 into the lunar regolith, which might be useful for fusion someday. All right, so how do we do this? First, we have to get moon rocks, okay? So luckily, the astronauts during the Apollo era had these awesome field trips where they bounced around on the moon and picked up rocks from the surface. And then later, I get to go to NASA and check out the moon rocks and pick out which ones I want. And then they come back to my lab, and we get these little tiny pieces, sometimes less than a gram, most of the time actually, less than a gram. And we get to do paleomagnetic studies on these rocks. And here's the workflow, okay? We start with the main mass at NASA. We pick out the piece that we get, very small. We cut that into even smaller pieces so we can do reproducibility studies. And then we measure the magnetization vectors, basically the intensity and directions of magnetizations in the sample. And if a sample's magnetized, you get this thing that looks like a line going to the origin. And if it's not magnetized, it looks like gobbledygook. Okay, so it's very simple to tell. And so the last thing, if we see a magnetized sample, is we want to ensure that these are lunar field records and not some kind of contamination from impact shock waves or cutting them with a saw dry or exposure to magnetic fields on Earth or a spacecraft or exposure to impact plasma fields. This type of quality checking work is all stuff that our lab has worked on significantly over the years. And so once we can rule out all these other things, we can construct a timeline of the moon's magnetic history. So each dot on this timeline is going to be a different rock. So I'm going to show you the rock that I showed you on the previous slide. So this is a 10071, Apollo 11, 3.5 billion years old. And it has a paleo intensity value of about, 20-something, 30-something microtesla. Okay, so then what we're going to do is yes. And then we have other samples from the same study that have different values. If it's red, it has a real value. If it's white with a down arrow, it means that we couldn't retrieve a magnetic field record, but there's an upper limit that we can impose based on the magnetic properties. Okay, so we can see that there's changes in the moon's magnetic field intensity in different samples. Why is that? That's another question that we're peering into it. And what we're finding is that rocks that have magnetic field records have this really interesting texture of the metallic iron grains, the magnetic carriers in the sample, where they have these subgrains. And the smaller the grains are, actually, the better the magnetic recorder they are. Whereas the samples that are unmagnetized don't seem to have this texture in TEM imaging. So we're working on that. This is our Doerr Discovery grant right now that we're working on. If we look at a lot of lunar rocks, we can really reconstruct this timeline and show that the early moon had a magnetic field that was very variable in intensity, but was there, and it persisted even for over 2 billion years. And this has not just been verified from the Apollo samples. This has actually been observed in the Chang'e samples within the past year that China collected from the moon. And so we can use all this information to say, okay, the moon had an ancient field, but like, what caused it? And so that's where modelers come in, and they have predictions for different mechanisms that could produce a magnetic field inside the moon. Some of them are conventional, like thermal convection of the moon. That's the short red line. That doesn't last very long, actually. You can have a thermochemical convection. That's the blue line for if an inner core started to crystallize and produce an additional power source of latent heat and chemical buoyancy, like the Earth's field does today. And then there's some other weird mechanisms, which I'll talk about on the next page, that might better fit the data that we see. So the moon might have had an esoteric dynamo mechanism because it's really hard to achieve the high intensities and the longevity of the field that we observe in the paleomagnetic record. So on Earth, we've had thermal convection, and once the inner core started to crystallize, we have thermochemical convection. But on the moon, a couple different things might have happened. You might have had big impacts that hit the moon and shake up the mantle of the moon, and that can actually cause mechanical stirring of the fluid in the core, and that stirring can generate a magnetic field. Alternatively, early in lunar history, when the moon was much closer to the Earth, because it's tidally recessing away from us over time, the moon's obliquity, or axial tilt, was actually much higher than it is right now. So that weird axial tilt and interactions, tidal interactions between the Earth and the moon could have actually caused the core of the moon and the mantle of the moon to precess like a top around different axes. And so the differential rotation of different layers within the moon can actually mechanically stir the core as well. And that could actually generate a pretty strong magnetic field. So all in all, we are choosing between convective and mechanical mechanisms. And it sounds like the mechanical ones might work a little better. But there's also a new contender in the race that maybe above the core of the moon, there's a layer of magma that was convecting. And that way, we can actually have a dynamo generated by conductive magma in the past. All right, paleomagnetism is one way to do this, but we can also study lunar magnetism using spacecraft and measuring what's in the lunar crust. So here's a magnetic map of the moon. And so this is from orbit, but if we really want to understand it, we got to get to the surface. And lately, we are able to do that because of commercialization of spaceflight. So the CLIPS program, Commercial Lunar Payload Services, is now delivering spacecraft to the lunar surface. This one that landed a couple weeks ago, the Firefly Blue Ghost lander, landed in Mare Crisium, which is one of the moon's big impact basins that has magnetic signatures inside it. And then next year, the Lunar Vertex rover, which I'm a co-investigator on, is going to land on the western edge of the moon, where this weird bright and dark optical feature exists on the surface. We don't know why it's there, but we know that the crust there is really, really magnetic, and that there's something about the magnetism that's causing the color difference, and we have to figure out what that is. And so our group's also written some papers trying to speculate on that as well. We've also been involved in planning a long-range autonomous lunar rover that could drive over 1,000 kilometers across the lunar surface and collect samples from multiple locations and bring them back to Earth. This would be Apollo-scale science if we can pull it off. And that's something that we are really excited about, and getting those samples and even making in situ magnetic measurements along the traverse. There's also a new opportunity to study Martian rocks that might come in the future, because right now the Perseverance rover is collecting samples on the moon to bring back to Earth. And the best part for me is that these samples are oriented, because they actually designed the rover to collect the sample with a known orientation that we can reconstruct. So not only can we get the intensity of the magnetic field, we can also get the paleofield geometry, which allows us to learn about tectonics and other problems, since we will have that information. So all in all, I'm really excited about paleomagnetism, obviously. It's what I do. And I'm really looking forward to seeing what our next rock will tell us about the solar system. Thank you.